Hi everyone. Today we're taking notes on section 4.5, which is the summary of curve sketching. So we're basically going to put everything we've learned in chapter 4 so far, increasing, decreasing, concavity, and all that good stuff to make really good sketches of graphs. So I'm going to make a list of all the things we know and all the things you should be utilizing to make a sketch. First of all, we should never forget to consider domain. Domain gives us the values of x that we can or cannot go through in a graph. You normally want to factor your function, okay, to see all the zeros or if any factors cross out for vertical asymptotes. 2, we've got intercepts. When I say intercepts, I mean x-intercepts and y-intercepts. And remember, for x-intercepts, we set the actual function equal to 0 and solve. And for y-intercepts, we plug in x equals 0 to see what the y value is going to be. We also have, I'm gonna put a question mark next to this just because we don't use it very often, but I'm going to include it in case. We have the symmetry test, which you learned about last year, and that tells you if a function is even or odd. Basically, whether a function is reflected across the y-axis or if a function has symmetry with respect to the origin, okay? And the test for that is if you plug in negative x into your function, okay, into all the x's of the function. If it spits out, if you simplify it and it does nothing to the function, it equals itself, then we say the function is even, so it's got symmetry with respect to the y-axis. But if you get the exact opposite function, we say that the function is odd and it has symmetry with respect to the origin. We can discuss that more in depth later. You use this only a little bit. Now, we've got a really important one, which is asymptotes. We know all about asymptotes. We have 3 kinds of asymptotes. We've got vertical asymptotes, which are domain restrictions that cannot be reduced. Like if you have a factor and you can't cross it out with another one, it's a vertical asymptote. We've got horizontal asymptotes, which come from limit as x approaches infinity, and you do the limit and you get some number. Or if you do limit as x approaches negative infinity of f of x, and you also get another number. Okay, the shortcut for horizontal asymptotes, shortcut, and that's only for rational functions, is to compare top degree to bottom degree. You know all of this, so I'm just making a list. And then we've got oblique asymptotes only when in a rational function, top degree is 1 more than bottom degree. And then we've got kind of under asymptotes, I'm going to add end behavior. Horizontal asymptote, oblique asymptote, those are end behaviors. So end behavior, and that's again a limit as x approaches to positive or negative infinity. And when you do that, if you get a number, that's a horizontal asymptote. L means limit. But if you get infinity, that means the end of your graph goes up. Or if you get negative infinity, the end of your graph goes down. Okay, so end behavior, that's a limit. And remember, we can use L'Hopital if we need to find this limit. We've got intervals of increasing versus decreasing, and along with that comes local maximums and minimums. And if you recall, this is all chapter 4. That's where you set your first derivative equal to 0. You find the critical numbers. So find critical numbers from f prime equals 0. Critical numbers. And then you make a number line with those critical numbers. And then you do your pluses and your minuses, you know. Okay. Number 6, we've got intervals of concavity. So number 5 was about f prime. Number 6 is about f double prime. Remember intervals of concavity, and so that deals with inflection points where concavity changes. This is where you set your second derivative equal to 0. You get the critical numbers of that second derivative, and then you do a number line to see if you have, you know, whatever. I'm just making up the pluses and minuses, but I'm doing that so I can remind you of number lines. And then 7, you put it all together and you sketch. You put all this information that you could potentially have about one single graph and you sketch it, and it's going to be a pretty exact sketch. I'm going to do one example on the notes with you, and then I'm going to do one example in class. So the example that I want to do with you is actually a rational function. So example, and that example is graph f of x equals x cubed over x cubed plus 1. And so I'm going to use some of the things on our list, maybe not all of them. First of all, I'm going to consider domain. Before I consider domain, I really want to have my function factored. So x cubed over, I notice that x cubed plus 1 is the sum of 2 cubes. And how does that factor? X plus 1 times x squared minus x plus 1. And so I can see that I have one domain restriction and I can't cross it out. So that means I have a vertical asymptote at x equals, it looks like -1. And this trinomial does not factor, so I will not get any real zeros from this. Excuse me. Then I've got the intercepts to consider. So intercepts, in terms of intercepts, let's do x-intercept first. Are there any x-intercepts? So you can take your factored function and set the numerator equal to 0, because it's a rational function, which means x equals 0 is an x-intercept. For y-intercepts, you set you don't set anything equal to 0, excuse me, you plug in x equals 0. So plug in x equals 0. And if you do that, I'll just do it here because it's shorter instead of this one. You get 0 cubed over 0 cubed plus 1, which is 0. So I've got, you know, a y-intercept of 0 and an x-intercept of 0. So that's actually the origin. I want to consider asymptotes. So since I have a rational function on my hands, I think I'm just going to do the shortcut instead of a limit. And I'm going to compare it top degree to bottom degree. I see that they are equal, x cubed over x cubed. So my horizontal asymptote is going to equal y equals leading coefficient over leading coefficient, which is 1 over 1. I've got a y equals 1 horizontal asymptote. So far, let's just recap what we have. We've got a vertical asymptote at x equals -1, just like that. And I've got a horizontal asymptote at y equals 1. And so I'm not going to bother doing a limit because I already know horizontal asymptote is end behavior. Okay, I know that the ends of this graph are going to skim y equals 1 to the right and y equals 1 to the left. Okay. Next, I want to do my increasing, decreasing, and concavity intervals. So I went ahead before doing the notes for you. I don't want to waste your time on the notes and go through the whole quotient rule with you to get the derivative of f, because I know everyone knows how to do that and that's an expectation of mine. So once you do, you know, the quotient rule on x cubed over x cubed plus 1 and you clean it up, you get a derivative that says 3x squared over x cubed plus 1 quantity squared. So I did the algebra for you, and this is the first derivative. And so for the first derivative, you always want a number line, okay? And you know, critical numbers are zeros and domain restrictions of that derivative. So it looks like in the numerator, x equals 0 will be a 0. And then how about from the denominator? Remember, x cubed plus 1, if you look up here, that factors into x plus 1, x squared minus x plus 1. This squared is that too. This is that. And so you'll see that I have 1, 0, and it is negative 1 again. I'm going to put in red as I go. Don't ever forget that x equals negative 1 is a vertical asymptote. This is not going to turn into a local maximum or a minimum. It will forever remain a vertical asymptote, but it still goes on your number line. And so when you do your pluses and your minuses test, you know, I actually went ahead and plugged in numbers before I did the notes too. You know, you plug in any number from this interval into the first derivative, it gives you positive. You plug in a number between negative 1 and 0. I happen to plug in negative 1/2 into the first derivative. I got something positive. And then I plugged in like a positive 1 into the first derivative, and I got something positive. What does this mean about my graph? That means it's increasing, and then increasing, and then increasing. So f of x is increasing over all intervals. This graph that we graph in the end will never decrease. It's increasing, followed by increasing, followed by increasing. Okay, now, we know negative 1 is a vertical asymptote, but what about 0? What about 0? Remember we discovered something about the x-intercept and the y-intercept. They were 0, 0. So when x is 0, we are going to cross through. We have a point. It is the origin, 0, 0. All right, now for the second derivative. So basically, we can conclude from the first derivative that we don't have no local maximum or minimum in this graph, okay? Because it never changes from plus to minus or minus to plus. It's increasing to increasing to increasing. That means no local maximum or minimum. Remember, when f prime changes from positive to negative or negative to positive, that's when we have a local max or min, and that doesn't do that in this graph. So I, again, before doing the notes, I went ahead and did the algebra. I did another quotient rule on this, the first derivative. I applied the quotient rule. You know, it was kind of messy, the whole algebra of it. But I got all the way down to this as my second derivative. Negative 6x quantity 2x cubed minus 1 over x cubed plus 1 quantity cubed. And it, you know, took a lot of simplification to get there, so I took my time. But anyway, this is the second derivative. So we definitely want a second derivative number line because that tells us about concavity increasing and decreasing. So we've got the critical numbers are the zeros and the domain restriction. So it looks like we've got 0. When you set 2x cubed minus 1 equal to 0 and you solve, you get x equals 1/2. No, sorry, x cubed equals 1/2, which means x is the cube root of 1/2. And if you punch in the cube root of 1/2, you get approximately 0.8. So I'm going to go ahead and put 0.8 on my number line. And then we've also got a restriction here. Remember, we've already done that. We've already factored x cubed plus 1, and we know that negative 1 is a restriction. So I've got 3 critical numbers on my number line, and I went ahead before the notes and I, picked a number from this interval. I picked a number from this interval. I picked a number from this interval, and I plugged a number from this interval into the second derivative. I used a table of values on my calculator instead of, doing it one by one. I plugged this function into y. Then I, asked the calculators, oh, plug in -2. Oh, plug in -1/2. Plug in 0.5. Plug in 1. And what happened was I got plus, minus, plus, minus. That means in terms of, because F double prime is about concavity, we've got concave up, concave down, concave up, concave down. Keep in mind, x equals -1 will forever remain a vertical asymptote. We already had 0, where was it? X and y intercept 0 and 0. We already had the point 0, 0. Now for the point 8, 0.8, comma, what point is that? You have to plug in 0.8 into the original to get a y value. Okay, f of 0.8, which will give you 0.8, comma, I went ahead before, the notes, I plugged in 0.8 into f on my calculator and it gave me 0.33. So I know this is a point of inflection point, IP. And so is this. Okay, now it's time to graph. You put it all together. So let me do a bigger sketch here and we're gonna be almost done here. I wanna plot all my, really important information. I've got a vertical asymptote at x equals -1. So here we go. X equals -1. We've got a horizontal asymptote. Where is it? Right here. Y equals 1. So here we go. Y equals 1. We've got our x and y intercept. They are the same, 0, 0. Did we have any local maximum or minimums to plot? No. We don't have a single local maximum or a local minimum. We just know that the graph is increasing the whole time. But we do have 2 inflection points to graph. We've got the 0, 0. Here it is. This is an IP. I'll just say IP so we don't forget. And we've got the 0.8, 0.33. So let's say this is 0.8 and this is 0.33. So I'll put a dot right here. This is the 0.8, 0.33, and this is also an IP, right? And now we're ready. There's nothing else to graph. We have to put it all together. So it says that the graph is increasing the whole way. The interval between -infinity and -1, this interval here, has to be increasing and it has to be concave up. This is the only option. This is it. Can't be down here because that would be decreasing and that would be concave down. It says the interval between -1 and 0, between -1 and 0, here and here, has to be concave down, but it also has to be increasing. Concave down, increasing. So it has to be down here. It has to look like that. Concave down, increasing. Concave down, increasing. It says the interval between 0 and 0.8, this one right here, 0 and 0.8, has to be concave up, but it also has to be still increasing. 0 and 0.8 is here, right? Increasing. So concave up, increasing. Look at that. So it does a little squiggle here. And then how about the interval between 0.8 and infinity? 0.8 and infinity, we are concave down, but we are increasing. The only option for that is to draw it like this. Skimming, getting closer and closer to the horizontal asymptote. How come it can't go up like this forever? Well, because we discovered that we have a horizontal asymptote in both directions. So it has to skim. How come it can't go above and then dip down? Because then it would go increasing and decreasing. And we know that we are never decreasing. So there it is. This is it. It goes up. It does a little squiggly thing here. So concave up, concave down, and then concave up, skimming all the way, skimming y equals 1 all the way to positive infinity. And this is our f of x graph. Happy, happy. Looks great. And we are done. Okay, we will do more in class on this. Thank you for paying attention and taking notes.